Hello everybody, this is Dr. Christopher White, and in this lecture we are going to be continuing with deformation and metamorphism. So in this lecture we're going to be focusing on the metamorphism. Alright, so let's get going. So we've already begun to investigate the processes of deformation, and now we're moving on to the metamorphism part. So we're going to think about the resulting rocks mostly in this case, because we've dealt with the structures. So we're going to have a think about and try and understand the plate tectonic settings of certain types of metamorphism. And we're going to have a think about how metamorphism is expressed in the landscape. Okay, so this is our rock cycle. We've seen it before. Let's just whip through this. So obviously rocks get weathered, producing a sediment. Sediment gets transported and of course eroded. Sediment gets deposited, forms a nice layer of sediment. That layer of sediment gets buried deeper into the pile, increasing pressure and temperature, leads to liquefaction. Of course, that produces a sedimentary rock. That sedimentary rock can then be uplifted to the surface, where it can be weathered again. However, if we keep increasing the pressure and temperature, we can eventually cause the sedimentary rock to metamorphose. Now, to be very, very clear, you can metamorphose any rock. You can metamorphose an igneous rock, you can metamorphose a sedimentary rock, or you can metamorphose a metamorphic rock, amazingly enough. So don't just think it's sedimentary rocks that get metamorphosed. Okay, and of course, so this is the portion of the diagram that we're dealing with here. And of course, then it can be uplifted and eroded, of course, the metamorphic rock, or we can bury it, increase the temperature and pressure further. That can possibly lead to melting. That will produce a magma. That, of course, will solidify, producing an igneous rock, which can then be uplifted and eroded, and the entire cycle keeps going and going and going. So, what are we going to have a think about? Well, we're going to focus on the concept of metamorphism, its importance, types of metamorphism, the causes of metamorphism, common metamorphic rocks, index minerals, facies, and plate tectonics. So, not much. Okay, so let's have a think about metamorphism first of all. Well, metamorphism is when a rock undergoes a change where it remains solid, and that's a very important point. A metamorphic rock has to remain solid. Now, during this change, there can be changes in chemical composition, there can be changes in the mineral content, and there can be changes in the physical texture of the rock. So sometimes the rock that you start with before metamorphism will look nothing like the rock which you end up with. And on the right here, you can see we have a picture of a type of rock. This is called a gneiss, and you can just see what an interesting pattern it has. It almost looks like a barcode that's been squished, doesn't it? So this is completely different to the rock that we started off with. Now, the changes that produce metamorphism are driven by increases or decreases in temperature and or pressure. Okay, so metamorphism goes two ways. Obviously, when we increase the temperature, that can cause metamorphism. When we decrease the temperature, that can also cause metamorphism. Because think about it. If you have a mineral that's present and it's stable at very, very high temperatures, and then we start taking that mineral and putting it into lower temperature conditions, well, that mineral is going to become unstable, isn't it? And so it's naturally going to start breaking down to form a mineral that is stable under those conditions. Now, in general, metamorphism is what we refer to as a deep-seated process. So it normally takes place in the lower crust or upper mantle. So it's not really something that takes place in the higher levels of the crust. Now, we know why that is. That's because the upper portion of the crust is, from a geologic point of view, relatively cool. And metamorphism on the whole typically requires temperatures in excess of about 200 Celsius. So metamorphic rocks, as I mentioned, can be created from all three rock types. And there are various degrees of metamorphism, which we refer to as high, medium, and low grade. So this diagram here kind of summarizes the general fields. I wish to stress this is a very general diagram. Okay? In general, metamorphism will begin if you take a rock above 200 Celsius. Between 200 Celsius and 700 Celsius, that's typically where metamorphic processes go on. Once you get above 700 Celsius, your rock will normally begin to become a little bit unstable and it will start melting, so we get some partial melting occurring. And then finally, once you start reaching temperatures in excess of at or in excess of 1200 Celsius, well, obviously the rock's going to become completely liquid. Okay, I wish to stress this is a very general diagram. It doesn't hold up for all situations. I should point out as well, during metamorphism, the rock must remain solid. So yes, the rock will change. Its chemical composition might change. Its mineral makeup might change. Its texture might change. But during all of those changes, the rock does not melt. Now, when I was talking a second ago about the different grades, what do I mean? Well, this diagram here kind of summarizes what's going on. So up here in this top corner we have lithification. That's sedimentary processes. So we're going to ignore that. We are looking at this portion here between low grade and high grade. So metamorphic rocks are split into low grade and high grade depending on how high the temperature and pressure was that they were exposed to. So if the pressure and temperature they're exposed to from a geologic point of view is relatively low, so let's just say something like, 225 Celsius. All right, 225 Celsius will kind of put you in this kind of region up here maybe. Okay, that's low grade. Those aren't very high temperatures, and so the minerals you produce will not be very, very high temperature metamorphic minerals. If, however, we'd start taking our rocks to something like, let's say, 350 Celsius, so we're going to take it to this kind of temperature up here, we're going to fall into intermediate grade, also referred to as medium grade, and in this case we're going to get higher temperature and pressure metamorphic minerals forming. And once we're up here in the high grade zone, let's say we take our rock to 600 Celsius, well, at that point the minerals we're going to form are going to be high temperature and typically pressure minerals. So you might have noticed what I kept saying was minerals, and it's the minerals that tell us whether we are in low grade, medium grade, or high grade. So as we move through this presentation, you'll begin to see there are some minerals that are lower temperature, lower grade minerals, and there are some minerals that are higher temperature, higher pressure minerals, which are typically found in high grade metamorphic rocks. Now, to be clear, typically a geologist doesn't refer to this kind of diagram. We just look at a rock and we just go, yeah, it looks kind of low grade, looks kind of high grade, looks medium grade. So, it's not a perfect breakdown. There's no real set boundary between these different fields. Okay, so let's just make that clear. But in general, as we move through the presentation, you'll begin to kind of get a feel for what low grade means, what medium grade means, and what high grade means. Okay, so when it comes to metamorphism, there are three different types. There is contact metamorphism, regional metamorphism, and subduction. Or shall I say, subduction metamorphism. So these are the three types of metamorphism that are most common. Now, the type of metamorphic rock that we get is primarily controlled by three things: the temperature, the pressure, which I've already mentioned those two, but arguably the most important thing is the starting rock. And the starting rock is referred to as the protolith. So the starting rock is obviously going to affect what type of metamorphic rock you get, because obviously the chemistry of that starting rock is going to affect the types of minerals you can form. Also, the types of minerals that you have in that starting rock are going to affect how easy or difficult it will be to metamorphose the rock. So if I have a rock that's full of clay minerals, well, that's a rock that's quite easy to metamorphose, so it will start metamorphosing at relatively low temperatures. In contrast, if I have a rock that's dominated by things like feldspar and quartz, so let's say something like a granite, well, that rock is on the whole going to be quite resistant to metamorphism. And so it's going to take quite high temperatures and quite high pressures before I begin to see any significant metamorphism of that rock. So the protolith, the starting rock, is actually super important in controlling the types of minerals that we see and the temperatures and pressures at which metamorphism will begin. So if we look at this diagram here, this diagram has three lines on it: a red line, a green line, and a blue line. Now these represent the paths, okay, which a rock being metamorphosed, should I say, can take. So the first path here marked out in red is the contact metamorphic path. So in contact metamorphism, we have a rock that's heated up by magma, typically in the upper portions of the crust. Okay, so we have a rock being heated up, so the rock's getting hot, but the pressure is typically quite low because we're dealing with an area that's quite high in the crust. So that means you can see what we have here is we have a line which is increasing in temperature across the top here, but the line is relatively low pressure. Pressure increases coming down here. You can see this line is increasing in temperature, but pressure is not increasing that much. Okay, so contact metamorphism is low pressure, high temperature. All right, what about the green line? Well, the green line is called regional metamorphism. Now, regional metamorphism is a type of metamorphism that covers quite a broad range of conditions. Okay, so as you can see, we are going essentially on a diagonal here, so we're covering a range of pressures and a range of temperatures. So regional metamorphism is extremely variable in its conditions. Typically though, when we start talking about regional metamorphism, we may well refer to it as high temperature, high pressure. Even though, of course, there are parts of the regional metamorphic line which are actually in relatively low pressure, low temperature conditions. But it's not uncommon for a geologist to refer to regional metamorphism as high temperature, high pressure metamorphism. Now, regional metamorphism we'll deal with in a second, but the fact it's called regional metamorphism should suggest that, number one, this metamorphic process happens over a very large area, and it's also got to be obviously related to quite large processes. So as you'll find out in a few minutes, it's due to mountain building in most cases. And finally, we have the blue line here. This is subduction metamorphism. And you can see subduction metamorphism is quite high pressure. You can see the pressures increasing quite quickly, but comparatively, the temperature is not. And we'll be discussing why that is. It's actually quite interesting. Subduction metamorphism is actually my favourite of the three types. It's quite cool. So subduction metamorphism is often referred to as high pressure, low temperature. So let's go through them again. Contact metamorphism, low pressure, high temperature. Regional metamorphism, typically referred to as high pressure, high temperature. Subduction metamorphism, typically referred to as high pressure, low temperature. And you're going to need to remember that because it's going to become important later on. Alright, so contact metamorphism. So contact metamorphism occurs when you have rock being heated up by a magma. There's a nice cartoonish diagram here in the top right that's just showing the basic process. You have magma coming in. Your magma could be at a range of different temperatures. I mean, it could be at 800 Celsius, 900 Celsius. It could be something rather hot like 1200 Celsius. And so what's going to happen is your magma is going to intrude the rock, and obviously it's going to heat up the rock that it's in contact with, isn't it? Makes sense. And so this rock is going to be exposed to high temperatures, but as we've discussed, the pressure is rather low because this is happening in the upper regions of the crust. And so from a geologic point of view, we consider that pressure to be low. Okay, so contact metamorphism is due to rock being heated by magma. So it's quite a local type of metamorphism. It's constrained. It has to occur along the edge of an intrusion, and that's it. So the heating will cause new minerals to form, or existing minerals to become coarser. So if you have a rock that's prone to metamorphism, well, the minerals in that rock are suddenly going to get very, very hot, and they're going to go, I don't like this. I need to change into a new mineral which is stable under these higher temperature conditions, and that's exactly what they'll do. Now, in some cases, you'll have a rock where the minerals are actually stable at these temperatures, so they'll be absolutely fine. But what the crystals will decide to do is, instead of having lots and lots of very small crystals, these crystals will then decide that the best thing to do is, even though they're stable at the high temperatures, they will decide that they're going to essentially begin to amalgamate, come together. So what will happen is you'll see lots of small crystals begin to change into fewer, larger crystals. So your rock will become coarser. Now, in terms of geology, we consider contact metamorphism to occur at a constant pressure. So the pressure is not considered to change. Now, this is because contact metamorphism typically occurs in the upper 5 kilometers of the crust. I'm going to refine that. Should be the upper 10 kilometers. And this is typically a region where stresses are lower. We know this is, of course, the brittle zone. So the metamorphic conditions are defined by high temperatures and low pressures, as we've already mentioned. And we've already discussed, as the rocks that surround an intrusion are quite poor conductors, that means the heat can't travel that far, so contact metamorphism is a very, very local process. So contact metamorphism is not extensive. So here's a picture that kind of summarizes the process. So here we have ourselves a sill, okay? And this sill looks like it's made of something like diabase. Okay, diabase is a type of rock that's related to basalt. Okay, it's a mafic igneous rock. So, okay, this diabase has been intruded into a sequence of limestones. We can see the limestone here. It's this fine-grained grey rock there, and it also appears down here below this blue label. You can't see it. Now, you will notice, though, that at the contact between the sill and the limestone, you'll notice just how white the rock is in comparison to the parent limestone. So what's happened? Well, the limestone here has obviously been heated up, and it's changed from limestone to marble. So two things have happened during this process. Number one, we have lots and lots of small crystals of calcite in our limestone here. When the limestone's been heated up, what's happened is all those small crystals have gone, right, what we're going to do is we're going to form fewer, larger crystals. So they kind of the rock has become coarser. The other thing that's happened is impurities in the limestone have essentially, for want of a better term, been boiled off by the heat of the intrusion, the magma that formed the sill. And so what happens is your rock here becomes much lighter in colour, because all those impurities, they're being boiled away. And so the rock you're left with here is a marble, which essentially is a coarser, cleaner version of a limestone. Okay, so I hope you understand the basics of what happened. So the marble here is our contact metamorphic rock. The limestone is the protolith, and the sill is the intrusion. So you can probably work this out. As we move away from our intrusion, the temperature is going to decrease, isn't it? The temperature is obviously going to be highest right here, next to our intrusion, and it's going to get lower as you move away from it, and eventually we're going to end up in temperatures which are background, the normal temperature for that set of conditions. So this means as you move away, the minerals are going to change. Right next to the intrusion, we're going to have quite high temperature minerals, aren't we? As you move further away, then we're going to have moderate grade minerals, then lower grade minerals, and then finally we're going to end back up in the unaltered rock. So this means we're going to have bands surrounding our intrusion, aren't we? We're going to have these rings around it. It's going to look kind of like a jawbreaker with the intrusion in the middle, then a high grade band around the intrusion, then an intermediate grade band or moderate grade band, and then a low grade band, and then finally you'll go back to the surrounding rock. Now these circles, these rings around the intrusion are referred to as aureoles. That's a technical term for them. So if we look at this diagram here, you can kind of see what's going on. So here's our sequence of rocks. Okay, this is what the rocks look like when they're unaltered. We've got a sandstone, a mudstone, a limestone, mudstone, limestone, mudstone, limestone, mudstone, limestone. Pretty standard sequence. Here's our intrusion, our granite. Now remember, at this point, our granite is, of course, liquid. So it's not a granite yet, it's just an intrusion of felsic magma. And the felsic magma is going to heat up this country rock. And so what do we see? Well, obviously we're going to have the highest temperature aureoles close to the intrusion, then the intermediate grade aureoles, then the low grade aureole, and then finally we're back to country rock. And what you'll notice is as you go from one aureole to the other, we'll see the minerals change. So in the mudstone, the shale here, what we're going to see is we're going to see changes in the minerals. So closest to the granite, we're going to have what's called pyroxene facies. because the mudstone here is going to alter to give us a rock that contains pyroxene. Okay, the fact that pyroxene's there, that indicates high temperatures, because pyroxene is a high temperature mineral. Now, as we move away and the temperature starts to get a bit lower, we're going to move into hornblende facies. So our mudstone here is going to have hornblende in it now. Once again, hornblende is an intermediate grade mineral. It prefers kind of lower temperatures than the pyroxene, but higher temperatures than the minerals we're going to form in this aureole. So the fact that we have hornblende in our rock tells us our temperatures are now kind of moderate. Now this rock, this aureole and the rocks in it will not contain pyroxene, because pyroxene only likes to occur in high temperatures. So its distribution will be limited, won't it? It can only exist in this aureole. Once you go out of this aureole, the pyroxene has to disappear and it's replaced by the hornblende, which is a type of amphibole. As we come this way, eventually the temperature is going to get so low that the hornblende becomes unstable, and instead the hornblende is replaced by a couple of minerals, one called albite, which is a type of sodium plagioclase feldspar, and another mineral called epidote. And so the mudstones here will contain albite and epidote in them, and that tells us the rock has been taken to low metamorphic grades. And then finally, as we move this way, we'll eventually leave this metamorphic aureole and we'll return to the country rock, which is at the normal temperature for the area. So you can see, by looking at the minerals, we can define in this instance these contact metamorphic aureoles. And the contact metamorphic aureoles, how we define them is based on the minerals that we see. These are the index minerals. So these are the minerals that tell us what's happening with regards to temperature and pressure. So what about regional metamorphism? So regional metamorphism is commonly associated with orogenies, so mountain building, burial, and migrating fluids. Now, there are slightly different types of regional metamorphism, but most of the time when we start talking about regional metamorphism, what we're talking about is mountain building. Now, mountain building, of course, results in two pieces of rock, two continents, smashing into each other. And so that means regional metamorphism is going to be associated with quite high pressures and quite high temperatures. Now this means we're going to end up with rocks which are quite interesting, because the fact that rocks are under those high pressures and temperatures means the rocks are going to naturally deform. So if the rock is ductile, we should expect to see lots and lots of folds. It also means that because we have these high pressures, if you remember when we're talking about deformation, if you squish the rock, if you have minerals which are long and slender, like the pencil here, or if you have minerals which are broad and flat, like this post-it note, it's quite broad, but it's actually not very thick at all. Okay. Well, those types of minerals, if they have those shapes, the pressure will naturally cause those minerals to align. And this means you will end up with a rock that has what we call a foliation. So there'll be lots and lots of very, very fine layers in the rock produced by all those minerals being forced to align parallel to each other. So regional metamorphic rocks often contain foliations. They are very often folded, and they're very often the rocks that are taken to the highest pressures and temperatures. So another thing to remember is, of course, regional metamorphism, as the name suggests, is regional. It can occur over large areas, talking thousands of square kilometers. So mountain building is the most common reason for regional metamorphism. It's most commonly associated with continent-continent and continent-ocean collisions. Not very commonly associated with ocean-ocean convergent plate boundaries. So, yeah. Okay, so these are the two standard areas in which we would expect to find large-scale regional metamorphism going on. Okay, so here we have a continent-ocean, and here we have a continent-continent collision. And you can see in both of these instances, we end up with a mountain range. And the mountain range is where it's all going on. This is where the metamorphism is taking place. And so you can probably work this out for yourself, but right down at the bottom here, we obviously have the highest pressures and temperatures, and as we get to higher levels in the mountain range, the temperature and pressure will steadily get lower. That's pretty obvious, isn't it? Now, that means regional metamorphism will have a range of different conditions, going from high pressure, high temperature here to lower pressure, lower temperature up here. So once again, we can expect bands, can't we? We can expect different bands which are based on different minerals, and of course those minerals will change as the pressure and temperature gets higher or lower. Okay, so here's a lovely example. Here's our mountain range. All right, now you can see we have these different bands, don't we? Okay, we have in this band here in purple, we have a band that's marked out by the presence of a mineral called sillimanite. Okay, sillimanite is a high temperature, high pressure mineral. It likes those conditions. Now then, as we start moving upwards through our sequence, we're going to get minerals which are stable at lower temperatures and pressures. So we go from sillimanite to andalusite, andalusite to garnet, garnet to biotite, and biotite to chlorite. Now each one of these is an index mineral. It tells us we're moving from the, tells us we're changing conditions, should I say. So what will happen is as we move from the sillimanite field to the andalusite field, we will lose sillimanite, because sillimanite can't exist in the same set of conditions as andalusite. So essentially, as we come across this boundary here, sillimanite goes away, andalusite appears. And that tells us we moved from one band to another, doesn't it? It's just like the contact metamorphic aureoles. So exactly the same process, but in this case it's just happening over a much larger area, and in this also it's related to mountain building. So once again, highest temperatures and pressures, obviously the deeper you go in the mountain, or should I say mountain range, and then as you get to higher crustal levels, the temperatures and pressures start getting lower and lower and lower, and so the minerals start to change. So for instance, we have minerals like andalusite and sillimanite, typically more associated with higher temperatures and pressures. We have garnet and biotite, typically associated with more moderate temperatures and pressures. And then we have chlorite, which is a low grade metamorphic mineral. And so you can see we're getting these different bands depending on temperature and pressure. Now, what happens? Well, one of the interesting things is when we essentially stop building our mountain range, when our continents stop colliding, the mountains stop forming. So think about it. The only reason that a mountain range is there is because we have these two pieces of rock bang into each other. And that pressure is essentially what's pushing our mountain range up. As soon as that pressure stops, well, what happens to the mountain range? It stops going upwards. And so the mountain range steadily gets eroded away. It gets eroded and eroded and eroded and eroded. And so eventually what will happen is our mountain range will be completely eroded away. So just to give you some idea, about 252-ish million years ago, down the eastern seaboard of the United States, there's the Appalachians. We probably know them quite well. Well, the Appalachian orogeny, okay, produced a set of mountains which would have been somewhat similar to the Himalayas. So 252 million years ago, down the eastern side of the United States, there would have been a set of mountains similar in scale to the Himalayas. By the end of the Cretaceous, about 66 million years ago, those mountains had been completely eroded away. So it took about 200 million years to get rid of them. So that gives you some idea of the kind of sizes of mountain ranges and the kind of time scales involved here. So in the case of the Appalachians, to go from a mountain range to a completely flat river valley took about 200 million years, give or take a little bit. But what else interesting happens? Well, the thing is as we remove the weight of the mountain range, the crust below pops up. It rises, it bounces upwards. No, so just think of a situation like you walking on a trampoline. When you stand on that trampoline, the surface of the trampoline dimples down, doesn't it, because of your weight? Well, as soon as you get off that area, the trampoline, of course, snaps back flat. Okay, that's what's happening with the crust. The weight of all the mountains above pushed down on the crust, causing it to warp downwards. As soon as that weight is removed, the crust will naturally bounce upwards again. Okay, called isostasy. So this means that these bands, which were part of our mountain range here, suddenly find themselves exposed on the surface of the Earth. And it's one of the fun things that the geologists can do is we can look for these bands in our areas of regional metamorphism, and we can essentially track what's happening. It's good fun. So we keep an eye out for these regional metamorphic zones. So here's a diagram that's going to kind of show you what's happening. So here is a picture. So we have New Hampshire, Massachusetts, Connecticut, Maine, New Brunswick, and then we're obviously into Nova Scotia, Prince Edward Island, obviously got Canada up here. Okay. So what are we looking at here? Well, these areas, these rocks have been classified based on the index minerals in the rocks. So you can see we have unmetamorphosed rock here in brown. You can see there's lots of that. Then we have biotite, garnet, staurolite, sillimanite, and then we have granitic rocks, so essentially magma. So you can see in this diagram over here, it's showing you the same band. So here we have essentially unmetamorphosed rock over here. Then we have chlorite, biotite, garnet, staurolite, sillimanite. The same bands we have here. So you can see as our rock goes this way, the temperature increases. So as we're moving from biotite to garnet to staurolite to sillimanite, the temperature is going up, isn't it? Yeah? Also, the pressure will be increasing because as we move to the sillimanite zone, as we know, we are finding ourselves in the core of our mountain range, aren't we? So sillimanite essentially represents the core of our mountain range right deep down. The staurolite zone represents being slightly further up. The garnet zone represents being slightly further up still. And then we have the biotite zone, represents slightly higher up, lower pressure and temperature conditions. So what we're seeing here is we're seeing the bands being produced by the regional metamorphic trends. So what can we see? Well, we can see the staurolite zone. We can see the staurolite zone here in orange. This essentially is the deep part of our mountain range. You'll also notice that it's got loads and loads of intrusions in it. And that's not really a huge shock. The deeper part of our mountain range is commonly going to be associated with lots and lots of intrusions. And so that's because the deeper part of our mountain range is often associated with, if we just go back here, magma. You can get magma moving up due to subduction, and you can get magma produced due to partial melting of the crust down here, right in the very, very deep parts of our mountain range. So the deeper portions of our mountain range are often quite magma rich. So we expect to find lots of intrusions associated with these high-grade rocks. Now, as we move away, remember, temperature and pressure is going to start getting lower because we are, in effect, going up for our mountain range. So what we're doing, we're starting off with sillimanite, then moving into staurolite. This yellow band, which we can see is ringing the sillimanite zone. Then we go into the garnet zone. So you can see it here. Here it is, this green band here. It's a little difficult to spot. The colour isn't very strong, but it's there. You can see there's the garnet zone. And then move into the biotite zone, which is here in purple. And then move into unmetamorphosed rock. So we can see this is the core of our mountain range here. And we're steadily progressing further and further into lower and lower crustal levels until we are in the unmetamorphosed rock. Now the thing you'll see is this metamorphism produced by this mountain range is covering a huge area, isn't it? It's covering several states. So this is not a localized process. This is a regional process, hence the name. Okay. So, do you know what? I've been going for 30 minutes, so this is a great place to stop. So once again, stop the video, have a walk around, get some water, cup of tea, cup of coffee, have a snack, and then come back for part 2, please.